Hello, this is Mr. Craig, and I want to talk about zero order reactions. I've already talked about first and second order reactions from the previous days. I want to talk about temperature and rate, collision theory, and activation energy. Let's first of all start off with zero order reactions or reactant. We've already talked about zero order reactants in that it is a reaction that regardless of what the concentration is, the rate remains the same. So I can double the concentration, the rate remains the same. I can take 1/4 of the concentration and the rate remains the same. So it's a really strange situation. I can't think of too many reactions that do have zero order reactants, but they do exist out there. And so again, the equations are given here, and what's really bizarre is this equation is not on the equation sheet. So what does that say about it appearing on the AP exam? Well, the concept will appear, but there won't be any math on the AP exam. So if you're wanting to find the half-life for a zero order reactant, the equation simply is stated: you take the initial concentration, divide it by 2, and that's equal to the negative KT plus the original concentration. Probably, in other words, just take the initial concentration divided by twice the rate constant K. You won't be doing any calculations with these, unfortunately. So, sorry about that, guys. At the bottom of the page on the front side here, I have a summary of all the rate laws, the orders, and the type of, especially right here, I don't know if I can highlight this, but this middle row right here probably is the most important thing that you need to know for the concepts when it comes to the AP exam and being able to determine the type of graph and what the order of the reactant is. Also, this next row here where it says the slope is negative K, and then for a second order positive K, that just reinforces this middle row here. So again, take what you want from this. For calculations, we'll only do first and second order type reactants. Alright, on the back side, let's talk about the relationship between temperature and rate. We've already talked earlier, and I can't recall when we did this, and I think it may have been with gases. That actually makes a little more sense. But the relationship between temperature and the rate of a reaction, if the temperature of the reaction increases, generally speaking, if it's not an equilibrium type problem, the rate of the reaction will increase. The reason why is because as we increase the temperature, we're increasing the amount of energy that's present with all the reactants, and they're able to find each other more quickly, collide more easily, and actually form the products. And we'll talk about collision theory here momentarily. But generally speaking, as the temperature increases, so does the rate of reaction. Temperature decreases, so does the rate of reaction. One general rule of thumb that isn't published too often, but I learned this in my organic class. As you increase the temperature of the reaction by 10 degrees Celsius, you typically double the rate. Now that has its limits, and there of course are exceptions to that. But if I double the temperature, if I increase the temperature of a reaction or of the system by 10 degrees, I can get the rate to double or become twice as fast. Also, if I place, say, the reaction in an ice bath to cool it down, if I could cool it down 10 degrees, then I could actually have the rate go twice as long. In other words, it's slower now. So yes, temperature and rate are directly proportional, generally speaking. Alright, collision theory. Collision theory talks about being able to collide correctly and form a product. In other words, just because one particle bumps into another particle doesn't necessarily mean that it's forming a product. It's kind of like pieces of a puzzle. The pieces of a puzzle will fit just correctly with the other piece. You can't force, well, you could force, but you don't want to force the two puzzle pieces together if you turn them, say, 90 degrees from each other and try to fit the pieces together. So when we talk about collision theory, it's all about making the right connection. And if this connection is not made, then the product is not formed. So, and again, when you increase the temperature of a reaction, you increase the possibility or the probability that they'll accidentally bump into each other in the correct way. Now again, by having those particles move around more quickly, that increases the chances that they'll collide correctly. Alright, activation energy and activated complex, and we'll talk more about this when we do thermodynamics, I think in the next topic or a couple topics from now. But when we talk about activation energy talks about the amount of energy needed for the reactants to change into the products, or the amount of energy that's needed to quote-unquote start the reaction. Actually, when I say start, I mean to have the reactants form products. So it's like the analogy that I use in classroom. I say, okay, on my desk I've got a big bowl of gasoline. If I take a match and I throw a match on the bowl of gasoline, what will happen? And oftentimes the students will yell, oh, it'll explode, it'll blow up. And then I'll say, no, the match isn't lit. So if I just throw a match on a bowl of gasoline that's not lit, nothing will happen, because it doesn't have that enough energy to get the reaction to start. However, if that match is lit and I now throw it on the bowl of gasoline, now we've got a light show. So the amount of energy needed for the reaction to take place means enough energy for the reactants to combine in the correct way to form the product. The graphs here actually show a couple different things. Typically the two graphs here on the right are pretty typical of what we talk about, and in other words, the reactants start off with a certain amount of energy, and then we need to add enough energy to change those reactants into products. And then on the other side, depending on if it's an endothermic or an exothermic reaction, it'll either be the amount of energy will be lower or greater than the amount of energy that the reactants start with. So we'll talk more extensively about endothermic reactions and exothermic reactions when we talk about thermodynamics. The graph here on the left actually shows or tries to represent which set of conditions or which temperature has more reactants changing into products. And the T's represent temperatures. Now often I'll ask the students, and they'll even see this T2 is greater than T1. I'll ask, which temperature is greatest when we look at this set of data here? And oftentimes the students will look to the left, but they don't realize that this E sub A represents the activation energy. The activation energy is this point right up here, or the amount of energy needed to change the reactants into products. So that's what this is right here. Once we've hit that point or that amount of energy, then the reactants have changed into products. So the blue line, or the T1 here, has a much lower temperature because more of the reactants are still below the activation energy, and there aren't as many that have changed into products. However, T2, more of the reactants are at a higher temperature and they have enough energy to change into products. So the T2 actually is at a much higher temperature than T1, and if you did a volume or an area estimate here, you would find out that the area is the same below each of these graphs respectively. Alright, looks like that's all I want to talk about for that page. I hope this has helped.